Dear students, this big machine you are looking at is an important part in the history of Indian engineering. You know why? This is the first machine in the entire Asia to produce electricity. Commissioned in the year 1905 under the leadership of the then Diwan of Mysore, Sri Sheshadri Iyer, the electricity produced by this machine was supplied to the gold mines of KGF.
The erstwhile Mysore state had the enviable and glorious position of establishing the first major hydroelectric generating station at Shivanasamudram as early as 1902 for commercial operation. On June 30th, 1902, just after the Mysore government approved the scheme of supplying electricity, KGF began receiving powers from Shivanasamudram. The falls at Shivanasamudram, created by the flowing Kaveri River, became India's second hydroelectric power station and Asia's largest. Also, the power which was generated here was supplied to the streetlights of Bangalore. Bangalore became the first city to receive electricity for the streetlights. Shivanasamudram is a small town which is located on the banks of river Kaveri. Here the river Kaveri falls down from a hill. This machine is kept for the viewers in the premises of the Institute of Engineers, Mysuru.
Dear students, in the previous chapter, we have learned few things about electricity and its heating effect. In this chapter, magnetic effect of electric current, we will learn about magnets and their properties. Relation between magnetism and electricity. Obtaining mechanical energy from electrical energy. Generation of electricity, like the machines that we saw just few minutes back. And lastly, we're going to learn about the steps to be taken in using electricity at homes. The foundation of science is to ask questions about the world around us and seek the answer for those questions. This topic is a perfect example for asking plenty of questions about the nature. While answering, we will do some experiments. Based on the results that we observe, we will frame a result, analyze it, improvise it by asking a new question and move to the next level. This is how we are going to learn this chapter. Let's begin to question. One thing that we observe about the magnet is that magnet attracts or repels another magnet. And they move. The magnets move on their own. We do not supply energy. So, can we use magnets to make other objects move? We want a lot of this form of moving, like in a fan, or a car, or a washing machine, things like that. We use this thinking thread and let's find a way of making things move with the help of magnets, but in a larger scale. But before that, we have to first recall few facts about magnets.
Magnets are of different shapes. For the purpose of studying their properties, in this chapter, we are going to consider three important shapes of magnet.
The bar magnet, horseshoe magnet, and magnetic compass, or we call it as magnetic needle. We know that magnets attract iron. Not only iron, also some other metals like cobalt, nickel, etc. Such type of materials are called magnetic materials. A freely suspended magnet settles in north-south direction. The one which shows the north direction is called North Pole, and the another which shows the south direction is called South Pole. Magnets have two poles. We represent North Pole by marking with a white dot. When we sprinkle iron filings near the magnet, we can observe that more iron filings attracted towards the poles. We can say that poles have more magnetic strength. When we bring north pole of the magnet towards the north pole of the another magnet, they repel each other. If we bring south pole of a magnet towards the north pole of another magnet, they attract each other. We can say that like poles repels each other and unlike poles attract each other.
From the properties of magnets, we got that they attract things like iron. Here is a safety pin near a magnet. Can the magnet attract the safety pin? Of course, but there is a limit for the distance from which it can attract. How far can we keep the pin to make it get attracted? There is a maximum area all around the magnet up to which the magnets attract the iron objects.
Let's keep the bar magnet on a sheet of paper. Mark the poles as N and S and sprinkle some iron filings around the sheet of paper. As the magnet attracts iron filings, we can see that the iron filings get arranged in a particular pattern. We can observe a particular pattern in the arrangement. This pattern is in the form of curved lines. These lines where the iron filings can be seen are called magnetic field lines. Remember, these lines are imaginary lines and they exist all around the magnet. The area where these lines are present is known as magnetic field. We can also use small compass to find the pattern of magnetic field lines. By placing many compasses around a bar magnet as shown, we can see that the magnetic field lines start at one pole and end at another pole. For convenience, we consider that it is moving from north to south around the magnet and from south to north inside the magnet. We just got few ways how we can visualize magnetic field lines. Let us study about these lines in detail. In order to do that, we have to draw these lines on a sheet of paper. Keep a magnet at the center of a white paper and mark its boundaries. Place a compass near the north pole of the bar magnet. The compass gets its south pole attracted to the north pole of the bar magnet. Mark a dot near the north pole of the compass. Now remove the compass and place the south pole of the compass near the dot. Repeat the same until we reach the other pole of the bar magnet. Now join these dots. We are going to get a curved line. Now try again, keeping the compass near the other places of the magnet. We get lines as shown. By observing these lines, we can infer that the magnetic field lines are emerging from north pole of the magnet to its south pole. These lines are curved and continuous. The magnetic field lines are parallel to each other, that is, they never intersect each other. The number of magnetic field lines per unit area or magnetic flux is more at the poles. That is the reason why the magnetic field strength is more at poles.
The concept of magnetic field and magnetic field lines explain the reasons for the presence of attractive or repulsive force and also the strength of magnet. These lines are different in their pattern for different shapes of magnets. If we are making use of any shape of magnets, it is necessary to get its magnetic field pattern. The pictorial representation of magnetic field lines is very useful for visualizing the strength and direction of the magnetic field.
So far, we found out the properties of magnets and the magnetic field lines. Let's quickly evaluate ourselves before we go to the next part.
Answer the following question. What will happen if two opposite poles of magnets are placed together? The options are: they will repel each other, or they will attract each other. Answer for this is they will attract each other. Now answer whether the following statement is true or false. The statement is: a magnet must touch matter in order to interact with it. Answer is: the statement is false. Now the next step is: the magnetic field lines intersect one another. The statement is false.
Magnets play an important role in various devices, which can be a small toy or a heavy crane to pick up heavy metals, or magnetic levitation trains, because they make the objects move. But small magnets like this will not help. How to produce powerful magnets? Let's find out.
You are looking at two pins made of iron. We know that they do not attract each other. When we bring a magnet near one of the pin, This pin comes inside the magnetic field and becomes a magnet. And we can see that it is behaving as a magnet. This can also be observed when a pin is attached to a magnet. The pin which is attached to magnet will also act as a magnet. We have two magnetic materials, a pin and a part of blade. If we keep on rubbing the blade in one direction with a powerful magnet, the blade gets magnetic properties and it starts to attract the pin. Another method of producing a magnet is this. We have wound insulated copper wire around an iron nail and let it connected to a battery. Be careful, if you are at home, connect only to the battery like this. When current flows through the wire, the iron pin gets attracted, indicating that the magnet can be obtained with the help of electricity. The magnetism in the nail lasts until the current flows through the wire. As soon as the current stops, the magnetic property of the nails also stops.
When we look at the last experiment, we found that as the current flows, the magnet is produced, and as soon as the current stops, the magnetism also stops. We can infer that there is a relation between magnetism and electricity. We will study about this link in detail through the following activities.
In this experiment, we have a battery, a wire which is supported by a wooden scale. We connect the ends of a wire to a battery through clips. We are placing a magnetic compass near the wire. It is well known that the compass rests in north-south direction. If there is a magnetic field created, it can be identified by the compass. Let us switch on the battery. You can observe that there is a deflection in the compass indicating a magnetic field is produced near a wire. Let us switch off the current, and there it is. The compass comes back to its original position. Let us continue the same by changing the direction of the electric current. When we switch on the battery, we observe that the deflection is in the opposite direction. When we compare the direction of deflection, the direction of the magnetic field also changes with the change in the direction of the current. From this activity, we can infer that a current carrying conductor possesses magnetic field around it. The direction of magnetic field depends on the direction of the electric current.
In 1820, Hans Christian Ørsted performed this important experiment accidentally, which proved that there is a connection between electricity and magnetism. By that time, the heating effect of electric current was well known. So, this effect of electric current, that is, a current can produce magnetic field, is called magnetic effect of electric current.
In the year 1820, Hans Christian Ørsted wanted to demonstrate the heating effect of electric current, where he passed electric current through a wire. Accidentally, he had a magnetic needle placed near the wire. When he passed electric current near the wire, he could observe that the magnetic needle which was kept near the wire deflected. This equipment in the tutorial models Ørsted's 1820 apparatus. The battery is a voltaic pile constructed of copper and zinc plates in a dilute acid solution. which you need not remember, a copper wire is held between two wooden clamps. If you can look at the compass, the magnetic needle is at north. Now we are going to switch on the battery. We can see that the compass has deflected. Ørsted tried this experiment with different polarities of the battery. He changed the direction of the battery and could observe that the magnetic needle or the compass deflected in the opposite direction. The picture here that you are looking at is believed to be the real scenario where Ørsted showed his experiment. After his experiments, Ampere, a famous scientist, demonstrated this in France in front of Ørsted and explained the science behind the magnetic field which is generated due to the flow of electric current around a conductor. This simple experiment by Ørsted proved to be a very important turn in the history of physics because it related electricity and magnetism, which were before him considered to be two different fields. Based on his experiments, we could create electric motors and generators later.
Newton once believed to be said, "If I have seen further than others, it's by standing upon the shoulders of giants." That is, finding of one experiment or one scientist is verified and improvised by other scientists and other experiments. Here too, we follow the footsteps of this method, use Ørsted's experiment to find some more results. Knowing that there is a magnetic field around a current carrying wire, we have to find the pattern of the magnetic field around the wire. Remember, we used iron filings and small compasses to find magnetic field around the bar magnet? We do that again.
Let us take a straight current carrying conductor and connect it to a battery. Spread some iron filings near the conductor and let us pass the current. Gently tap the surface on which iron filings are spread. Gradually, we can see that the iron filings spread themselves in a pattern. This pattern resembles that of a concentric circles. So we can say that when current flows through a straight current carrying conductor, the magnetic field will be in the form of concentric circles, which looks like this. But how to decide the direction of magnetic field around a straight current carrying conductor? In order to do so, let us take small compasses and place it over the surface which is perpendicular to the current carrying conductor. We can see that all the compasses are arranged in different directions. When electricity is passed through it, we can see that all these compasses will align themselves in a particular order. Here, they have arranged themselves in anti-clockwise direction. When the current moves upward, the magnetic field lines are anti-clockwise. Let us change the direction of electric current by changing the terminals of the battery. Let us pass the electric current. Now we can see that magnetic compasses align themselves in a different direction. Now they are clockwise. When the current moves downwards, magnetic field lines will be in clockwise directions. So we can say that the direction of magnetic field depends on the direction of electric current.
So far, we learnt that a current carrying conductor creates a magnetic field around it, which can be comprehended by using magnetic lines of force or magnetic field lines. The nature of the magnetic field lines around a straight current carrying conductor is concentric circles with center at the axis of the conductor. Let's quickly evaluate ourselves before we go to the next part.
After learning many things about Oersted's experiment, let us test our understanding about Oersted's experiment. Which of the following statements is true? There is no relationship between magnetism and electricity. Current produces magnetic field. Compass is not affected by electricity. Compass is not affected by a magnet. Correct option is current produces a magnetic field. On reversing the direction of current in a wire, magnetic field gets reverse in direction, increase in strength, decrease in strength, remains unchanged in strength and direction. The correct option is gets reverse in direction. The strength of magnetic field produced around the current carrying conductor is proportional to direction of current, magnitude of current, both A and B, none of this. Option is both magnitude and direction.
What is magnetic field? Draw a diagram showing the magnetic field pattern due to a straight conductor carrying current. State any two properties of the magnetic field lines. State whether the following statement is true or false. In the bar magnet, magnetic field is weak at the poles. A current flowing in a wire always gives rise to a magnetic field around it.
If you look at one key point from this session, we could get a method by which we got artificial magnets from electric current. In the next session, students, we are going to learn how to make these magnets more powerful magnets. We know powerful magnets can make the things keep moving. More powerful magnets keep them moving more and more.